All right, so today's plan is to finish up Chapter 5, just about all of it. There is some Chapter 5 homework due tonight. There's also some Chapter 6 homework due Wednesday, so we should hopefully get through enough Chapter 5 so you're ready for Wednesday Chapter 6. If not, I'll move all the Chapter 6s ahead by a day if we don't get to it by today. I do have all the exams graded. The grades are on mastering. I'm not able to pass back the exams yet because not everybody has taken the exam. So as soon as I get everyone to have taken the exam, I can pass them back. But if nothing else, your grade is on mastering, so you can at least see how you did. Fair enough. And a group quiz Friday. All right. Let's talk about using density with the ideal gas law. So let's determine big M, which is the molar mass. And the molecular formula of an unknown compound that contains iron and oxygen, given that the density of the gas is 23.13 grams per liter. At 375.5 Kelvin and 8.21 atmospheres. All right, so the equation we had at the very end of class the other day was density equals pressure, molar mass, gas constant, temperature. Which one of those things are we looking for again? Molar mass. So the best way to do this is to rearrange the equation so that the molar mass is all sitting by itself. So if we do that, we end up with density, gas constant, temperature over pressure equals molar mass. Have I given you all the things you need in order to plug it in? I have. Let's get out our calculators because you'll need them several times today. So if you don't have them out on your bench top, you will need to fetch them out. All right, so the density was given in 23.13 grams per liter. The gas constant is a constant that's given other places. Then the temperature. All right, how do I look unit-wise? Let's move my pointer. I'm good, right? Because liters and liters, atmospheres, atmospheres, Kelvin, Kelvin. I'm going to be left in grams per mole. Is that a reasonable unit for molar mass? It is. All right, so I'm going to double check my math. I'll use my calculator over here. What are we getting about? 86. That's what I got. 86 was like 86.8, somewhere in there. Grams per mole. All right, so that is part one. That's the molar mass. So then the second part is figuring out the formula of the compound that contains that much iron and that much oxygen. So, iron has a molar mass of 55.8. Oxygen is 16. So now we're looking for a combination of iron and oxygen that has that molar mass. So what if I did a 1-to-1 ratio? 1 iron, 1 oxygen. How much would that weigh? Like 72, right? All right, so FeO is around 72. Is that pretty close to what we want? No, that's not good. What if I do double the oxygens? It has to be 72 plus number 16. Like on the order of 88. So how is that for a molecular formula? Pretty good. Based on what you guys did in the carbon dioxide lab, that's fairly reasonable, right? Because this is pretty much the exact same experiment you just did, but instead of carbon and oxygen, it's iron and oxygen. Look at that, lab and lecture coming together, interrelated. Yeah, should blow you up like that. Okay, good. Any questions on how to do those kinds of problems? Okay. In that case, let's look at gas stoichiometry. So, as a reminder, stoichiometry is the way that we figure out the coefficients so that there's as many reactants as there are products, right? So we did some balancing equations a few weeks ago. Stoichiometry is just the numbers that goes with the balancing. So stoichiometry for a gas reaction is the same as if it were a liquid or a solid. We'll use the balanced chemical equation to solve for unknowns. And just as a reminder, in case you forgot, amount of reactant, convert to moles of reactant, convert to moles of product, convert to amount of reactant is our in general way to do that. Okay. Just review, just in case you've forgotten. Hard to believe you would have forgotten, but just in case. So what is the volume of carbon dioxide produced at 37 degrees Celsius in 1 atmosphere when you have 5.6 grams of glucose reacting with oxygen in the following equation? So, first question you have to ask yourself, is this equation balanced? Did I try to trick you in any kind of way? I think I did. I think it's right this time. I think I fixed it from last year. Good. Step 1. Good. Always check. Yeah. So check if balanced. Good. Then the second thing, we are looking for volume. So using our ideal gas law, right, our PV equals nRT, we're looking for volume. So we need to rearrange it so volume's by itself. So R is the gas constant, temperature is given, pressure is given. What about that N? What is N? Number of moles. Do you know the number of moles yet? No. So we have to find the number of moles of carbon dioxide given grams of glucose. Okay? So you may want to do this on a separate piece of paper or off to the side because we'll plug it in later. So let's see if I have a piece of paper. So we need to figure out the number of moles of carbon dioxide. So we know we have 5.60 grams glucose. In the end, I want to be in moles of oxygen. So what's the first step we need to do to get from our grams to our next step? Molecular weight of glucose. Okay, happens to be 180. It is, that's why I use it. Alright, so now I am in moles of glucose. What is my next step to get to moles of carbon dioxide? The ratio. So I have 1 glucose for every 6 carbon dioxides. So do I put the 1 on top or the 6 on top? 6. Why do I put the 6 on top? That's what I'm trying to get to. Just a good review. Do I have to do anything else? No. There's a common error to go one more step, because if it was like a regular liquid or solid equation, I'd want to know the mass. I do not want to know the mass. I just want to know moles. So stop right there. And we'll see how many moles that is. Everybody get something in that ballpark? Okay. So now we are ready to plug back into our volume equation. What's the last thing? I gave you temperature in Celsius. Trying to trick you. What does it have to be in Kelvin? So let's see. Everybody get 4.76 meters? Okay. Questions on how to tackle these problems? This is very similar to what we have been doing. It's now just looking at gases rather than solids, liquids. Alright, in that case, let's move on to the tricky part of the chapter. Mixtures of gases, partial pressures, and the kinetic molecular theory. You know, it's not tricky. You haven't seen it before, that's all. Alright, so here are some definitions that we'll need for later. So, partial pressure is the pressure of individual gas components in a mixture. So each gas contributes its own pressure to the total sum of the pressure. So all the partial pressures in a mixture sum together to make up the total pressure of the gas. Dalton's law is what we use to define the total pressure of a mixture. And pretty much it's the sum of all the pressures. Sum of all the partial pressures is Dalton's law. So those can be used interchangeably. And the last one that's kind of a crazy idea to think about is mole fraction. That expresses the ratio of the number of moles of one component to the number of moles of all the components. So I could say the person fraction in here, if I was going to say people wearing white shirts, People number of white shirts divided by total number of people in here. So it looks like it's 1. 1 white shirt in here today. So 1 out of what in theory should be 40 people. Looking a little thin today. So 1 out of 40, right? Dimensionless quantity, fraction over the sum. Good, good, okay. So here's my fancy diagram about partial pressures. Worked real hard on this. I have this container, which has a pressure of not very much. We'll say that's 5 atmospheres. I have this container over here, which has, we'll say, 12 of pressure in it. If I were able to squish those 2 containers together, or dump all the molecules into one container, assuming that the container didn't change, and I didn't do anything crazy to the room temperature, this new pressure would be the 2 pressures added together. That should intuitively make sense, right? Pressure 1 plus pressure 2 equals total pressure. How do we use that mathematically with our ideal gas law? So we just all agreed that the total pressure is the pressure of 1 plus the pressure of 2. And this is the ideal gas constant, or ideal gas law. I could say the following. So the pressure of 1 using the ideal gas law, assuming that the containers are constant, the gas constant's a constant, temperature's a constant, that pressure 1 is related to the moles of 1, and pressure 2 is related to the number of moles of 2. Same container, same temperature, gas constant's constant. So then I could combine those together All right, so far I haven't done anything crazy. Just rewrote what we had. So now we're going to do some crazy algebra. Ready? We're going to do the common factors. We're going to factorialize. Is that what you guys call it in math? Factorize? Factor out. Yes, so I'm going to factor out the things. I heard that someone whispered it. I obviously don't teach algebra. Ooh, that blow your mind right there? Pretty crazy, right? And 1 plus n2 times the things they're all constant. In fact, I'll even go one step further. Whoa. N1 plus N2 is all the moles, so I'm just going to call those total. Good so far there. Everybody followed my incredibly tricky math. Excellent. Now, that is good if I know the individual pressures. You may not know the individual pressures. You may only know the mole components, and you want to find the total pressure. I wrote real big, so this is still on the same page. So sometimes they write it in one way where you know all the moles and you're looking for the total pressure. Sometimes they write it the reverse, where you know all the moles and you want to know the individual pressures. So going back to our starting point, I could do some of the following crazy algebra. So far, so good. Or I could do the following. That's what we just had from the previous page. Right, just dividing, both of which look okay. What can I do? I'll focus on this one. What can I do now on this to simplify it? Mm-hmm. So now I have the pressure of one over the pressure of the total is the number of moles of one part of it divided by the total moles. Thinking back 5 minutes ago, what did I say that new ratio is called? It is the mole fraction. And for whatever reason, the mole fraction is given the big symbol X. And little 1, because in this case, this is the mole fraction of component number 1. And the more usable form of that is that the partial pressure of component 1 is equal to the mole fraction of 1 times the total pressure. Which should make sense, it's right, because volume, temperature, and the gas constant are all being held the same. So the partial pressure of 1 is really only affected by how many moles of 1 are in your component. So that is all awesome. So let's put it to use and see how it works out. So let's say you have a sample of natural gas. It contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If you know the total pressure of everybody altogether is 1.37, I want to know the partial pressure of just the propane component. So, first thing we need to do, because we're headed towards this, that's the equation we want to use. I want the partial pressure of component 1, the mole fraction of that, total pressure. Do I know the total pressure? Yes, I gave it to you. So we just need to find the mole fraction. So the mole fraction definition was number of moles, the component I want, over total number of moles. So how many moles of just C3H8 are there? How do I figure out how many total moles there are? I'm just going to add them all together. Would mole fraction have any units? Where are the units on top of my mole fraction? Where are the units on the bottom of my fraction? Cancel out, no units. So it's moles per mole. So it cancels out, no units. All right, so now we're ready to plug it in. And what would be the units of my partial pressure? In this case, atmospheres. Okay, what if I follow up this question with what's the partial pressure of, let's do another one, let's do CH4. Let's go ahead and work that out and see how that. Do you expect its mole fraction to be greater or less than the mole fraction of propane? Greater. How do you know it's greater? Right, it's the majority component, so you expect it to be a much larger. Everybody agree with my math? Is there something a little funky? Oh. Okay. Let me ask 2 follow-up questions to this. If nobody disagrees with my math, I sit on the fly. Okay. What do you think the mole fraction of the CH2H2 component should be? Without doing any math, how would you know what it is? Right? So mole fractions must add to 1. Right? A whole fraction is 1. So in this case, we know that mole fraction of C3H8 plus 2H6 1. I know of 0.93 and I got 0.0132, so that's not right, hold on. Oh, that's fine. Somewhere in there. But let's say I didn't want to do that part. I just want to figure out what P3 was. I know the total pressure. I know two of the 3 parts in there. So this must be 1.37 minus 1.27 minus 0.011. All right, so 2 takeaways. 1, mole fractions all add to 1. So if you know most of the mole fractions, you can figure out whatever's left. And it's a good way to double check your math to make sure you're doing it correctly. The total pressure is equal to all the partial pressures. So if you know most of the partial pressures, you can figure out whichever ones are left that way. How am I feeling about partial pressures? It's kind of using what you already know, just kind of recombining it. All right, so then let's talk about the last thing in chapter 5.5. Which is this thought experiment called the kinetic molecular theory. So gas laws help predict the behaviors of gases, but they are not able to exactly predict what's happening at the molecular level. And so we know that hot air rises, and we can predict the results like we did in Charles's law on Friday. But why is hot air less dense? Right? So we know it is, and we can mathematically prove it, but why is it? Also related questions. These are all questions that we all know are true. Like tires get colder, or when the temperature is colder, your tires deflate, which if you haven't checked your tires, now that it's gotten to be cold, do that to make sure you're not driving on underinflated tires. My little health warning for today. And the second one is, why do fish need a bubbler in a tank? They don't have to have one depending on the type of fish, but most fish prefer to have an air bubbler of some sort. So, so do I have this on this page or next page? I'm going to do two things on here. So molecular movement is a form of energy, right? What are the two typical forms of energy we usually talk about? Kinetic and potential, right? We're going to be talking about the kinetic. And kinetic is referring to what sort of motion? Moving, right? Any kind of motion, like not standing still, moving. What is energy typically measured in what unit? Joules. Good. We'll be using joules again. So we're going to use the kinetic molecular theory to explain gas movement. So there are four main components, and I wrote them out, so I'll go real slow for those of you who are writing out your hand notes. So firstly, gases are composed of molecules that are physically separated from each other by distances far greater than their own dimensions, right? So an atom by itself is only a few nanometers across, maybe if it's huge, but the distance between two molecules in air is on the order of like, could be as many as millimeters, right? Tens of orders different. So they're much smaller. They can't always see their next door neighbor. So we consider the molecules points in space, that they have mass, but they have very, very small volume. Everybody on board with that? Fairly straightforward. Okay. Gas molecules are in constant motion, and the motion is in random directions. It's not predictable. As such, they frequently run into each other. We call those collisions. And the collisions are elastic. What does it mean to have an elastic collision? Anyone who's taking physics? Yep. So here's my picture of an elastic collision. It's kind of like you can imagine two pool balls. I don't know if people still play pool. Like they run into each other, and in theory, you could bounce off completely from each other. They treat like that. This would be an inelastic collision where they get stuck. So we imagine that all gas molecules are perfectly elastic. They're zipping around space, bouncing off of other people and molecules. Gases are neither attractive nor repulsive, which means when they bounce into each other, they're not looking for someone else. They're also not repulsed by anyone else. They're just randomly bouncing around. This is like the big one though. The average kinetic energy of all the molecules in a gas is proportional to the temperature. So if you're thinking about that, it means the hotter you get, the more energy you'll have. The colder you get, the less energy you'll have. Two gases at the same temperature, so if I had 2 beakers of gas sitting up here, we're all at the same temperature, so they should have, in theory, the exact same amount of kinetic energy. Those are like the ground rules for this. Okay? So, using what we know, the gas laws, and those 4 postulates, we can see why gases behave the way that they do. So according to the kinetic molecular theory, particles of different mass have the same kinetic energy at the same temperature. So here's my kinetic energy. I'm like 3 or 4 days behind lab because I know you guys did this in lab too, the lighter and heavier molecules. So kinetic energy equals 1/2 the mass of the molecule times the velocity squared of the molecule. So given a gas, if kinetic energy is directly proportional to mass, particles that are lighter will travel faster than heavier ones. Which, you guys, is what you did in your pre-lab question. Oh, and also the diffusion, where you had the hydrochloric acid and the ammonia. You saw that the ammonia was lighter, so it traveled faster and got to the other product, the other liquid. Okay, good. So here we have a distribution of speeds of 3 different gases at the same temperature. So I have helium with a mass of 4. Nitrogen with a mass of 28 and chlorine with a mass of 70. The lightest gas is helium, and its average speed is a little over 1,000 meters per second. Pretty fast, pretty fast. This is at 300 Kelvin, so a little over room temperature, a little on the toasty side. Nitrogen has a speed of about 500 meters per second, and then chlorine's the heaviest, so it's the slowest, if you want to call 250 meters a second slow. But on the scale, it is the slowest of the 3. Right, just like you did in pre-lab. Now the second part is, what if I have one gas at a few different temperatures? Right, so this is several gases, one temperature. What if I have one gas, cold, warm, hot, the Goldilocks principle? Right, which one's just right? No? No. So the second half says the average kinetic energy is proportional to temperature. And I could go through a long derivation as to why we get to this equation. It's in your book. We're fascinated by derivations, but kinetic energy is 3/2 RT. So you can say kinetic energy is proportional to temperature, which means as the temperature rises, the kinetic energy increases. If the kinetic energy increases, it can move faster. And just on the other page. That kinetic energy is inversely proportional to molar mass. As it gets heavier, slower. So here is, hard to see, there we go. So here I have nitrogen at 3 different temperatures. At 100 Kelvin, it's moving like 250 meters per second. As it gets hotter, it moves faster because it has more kinetic energy, which is kind of what you already know, just mathematically showing it to you. Fair enough. I will save this last problem because we don't have enough time to finish it. So I'll save this for Wednesday and bring your chapter 6 notes with you, and I'll move this mastering since we haven't started chapter 6 yet. I'll change it to Friday. So I'll just move all the homeworks forward. You finished everything you need for chapter 5. Since we haven't started chapter 6 yet, I'll move chapter 6 homework. Yeah, Wednesday's not Friday. Friday will be Monday.